Well, pre-calculus classes, as always, good morning, good afternoon, or good evening. We will go ahead and finish up section 3.5 here today. I know I'd mentioned it's at the end of 3.4 notes that we really aren't going to look at anything new in 3.5. It's mostly going to just be some application and modeling within exponential and logarithmic models. So we'll go ahead and certainly talk a little bit about, the exponential growth or decay model. A equals a sub 0, which is your initial amount, times e to the kx. Basically, this is just an example of the PERT formula. If k is positive, you have a growth model. If k is negative, you have a decay model. You can't have 0, otherwise you would just have a horizontal line, as that would make the e to the kx equal to 1. So, a sub 0 again, in addition to being the initial amount, that is the y-intercept. I know we looked at a problem back in the beginning of chapter 3 with the fruit flies, and that's something I even kind of mentioned at that time, but that's when the time is 0. So here we have a population growing by the model P of t equals 5.3 e to the 0.013819 t, where P is the population in millions, t equals 0 represents the population in 1990. If the original population was 5.3 million, when will it be 6.5 million? So, again, basically, the 6.5 million, that's your final amount for A. The A sub 0 or initial amount is 5.3. And don't worry about writing in all the zeros. E to the 0.013819 t. So, from here, again, now we're just going to solve an exponential equation. So divide the 5.3 and 1.226. Now, one of the things I'm going to say is I'm going to write out this. Don't clear your calculator out, though, because that way you can use the entire decimal that's in there. So now to certainly get rid of e, we'll take the natural log of both sides. And when you do that, now what you can do is, as you take the natural log, if you press second and then the negative button, that will use that entire decimal. So it's the second answer function. And so now we end up with 0.204 equals, again, allows us to move out to the front, 0.013819 t, and then we can divide by that. And again, now you are just hit divided by. Okay, so let me get back to this. Okay, so now I'm going to divide that. 5.013819 and 14.77 is t. Now, here's where you do have to be careful. The question is, when will the population be 6.5 million? Well, it's 14.77 years after 1990. So, if you add 14.77 years on, it would be during 2004. it'd be towards the end of 2004, probably September, October. You don't have to be that exact there. But that is the one thing that you do need to be careful about is, okay, make sure you actually answer the question and don't just find the variable. For example, 2, honestly, we've done something like this one already, but $600 is invested in a continuously compounded account. Again, there's your keyword. Grows to $19,205 after 10 years. How many years did it take for the initial investment to double? Well, this does actually have 2 parts to it. So, because what you are going to have to first do is find the rate, because right now we don't know what the rate is. So we know that's our final amount. That's our initial amount in PERT, and then the rate times 10. So from here, first divide the 600. So 32.008. Again, keep that amount in your calculator. And then I'm just going to make that 10R because that looks mathematically better. So again, to get rid of E, we'll take the natural log. So 10R equals natural log of 32.008. And then we'll divide. So natural log of that answer divided by 10. So actually, this ends up being a very large interest rate. So let's go 3, 4, 7, or actually let's even go 3, 4, 6, 6. That'll actually be a little more exact as we go from there. So the first thing we needed is our rate. Now we can use this to figure out how long would it have taken for that $600 to double. Well, at that interest rate, I can tell you it won't be very long. So 1,200 equals 600 times e to the 0.3466t. Well, here, divide by 600, and so now it's just 2 equals e to that, and then we'll take natural log, and so the natural log of 2 equals 0.3466t, and then your last step is to divide. And honestly, since the nice thing about it doubling, really don't even have to enter anything into our calculator. Now we can just take the natural log of 2 and actually divide it by that value there. That's one of the reasons why I don't clear things from my calculator, because a lot of times you can use that exact value, which just gives you a slightly better answer. So you can see that it's basically 2 years. And that's one of the other reasons why, if you don't clear things out, gives you a little better answer in the end. So it takes about 2 years, again, even though it didn't specifically say that you kind of had a 2-part question here, we did. All right, example 3, fruit flies. Growth can be represented as continuous exponential growth. After 2 days, there are 100. 4 days, there are 300. How many will there be after 6 days? Well, again, here is where we are going to have to kind of set this up in 2 parts. So, after 2 days, there are 100 flies. Well, we don't really know what the initial amount actually is, so we're going to actually use this as our initial amount to help us find the growth rate. So the 300 is like your A, the 100 is your P, e to the, and then R times 2. So again, we'll divide by 100. So 3 equals e to the 2r. And then we'll take natural log. So the natural log of 3 equals 2r, and then we can divide. .549. All right, so now how many will there be after 6 days? Now here's where you do have to be a little careful. You can either use the 100 or the 300 as your A. You just then have to be careful about, okay, what will we use as our time? If you go ahead and use the 100, e to the 0.549, because they want to know after day 6. Well, this was day 2. So I would do times 4. I could use the 300 there, and since that was after day 4, then I would have used times 2 here. So again, that's really the only thing you do have to watch for on that. So 100 second E, and now again, here's where I can just actually go ahead and use that answer times 4, and ends up being 900 flies. So, you know, if you'd use 300 there and 2, you'd end up with the exact same answer. So, now, one of the other things, too, you might even notice is over a 2-day period, it is tripling. So, although in theory, chances are some of those will die off, my guess is the life of a fruit fly is fairly short. But that is another example there. One final thing, and this is why I said there's not a lot of new material. And this example is ironically very meaningful right now, but a logistic growth model. Kind of an ugly looking equation here. Y equals A over 1 plus B times e to the negative RT. A is your population size, T is time. On a college campus of 5,000 students, one student returns from vacation with a contagious long-lasting flu virus. The spread of the virus is modeled by this equation, where Y is the number of students infected after T days. The college will cancel classes when 40% or more of the students are infected. Chances are it would be a lot less than that. But anyway, for the sake of this example, that is what we're using here. Now, the first thing that it does say to do is enter it into the calculator. So Y equals 5,000, and then in parentheses, first make sure you divide. 1 plus 4999 e to the negative 0.8 x, and then just to be on the safe side, I will go ahead and close every parenthesis I open. Now, again, one of the things here that we are going to have to look at is an appropriate window. So from here for our window, the x minimum, honestly, you could make that 0. The x maximum, kind of hard to say. The y minimum is 0, and then the y maximum, is technically 5,000. I'm even going to go a little above that just so you can see. And when we graph this, okay, we actually are going to need, because it looks initially like it's exponential growth. So what we're going to need to do, I'm going to go back and let's change our x max to 50 just to see what happens. Okay, so here's what you can see is, when you have a virus, now this is like worst case. I mean, it grows exponentially. I mean, and then once you get here, this is saying, hey, the entire student body has it. Now, obviously, they're going to do something to try to, again, using terms you've heard in the news now, they want to flatten the curve off, and certainly before it reaches the point of everybody having it. But that's what a logistic model looks like. It grows exponentially, but then you get to a point where it flattens out because, that's the entire population. Again, you always want to flatten it before you get there, but anyway, that's, kind of some of the math involved with certainly what we've seen in the news here in the last, year. All right, so how many students are infected after 5 days? Well, the way we're going to do that, if you want, you can even go into your table. After 5 days, so again, what I did there, second graph pulls up my table. Well, after 5 days, about 54 students. Otherwise, you just plug 5 into the equation. And so right now, this would even be the point where, like, whoever had this probably didn't even know they came back with it. And again, at 54 students, the campus isn't going to really notice a lot. That's such a small percentage of their student body. After how many days will the college cancel classes? Well, now is where, again, you can still on your table, 40% is 2,000. So let's take a look and just see on our table. It's only going, but you can see it's growing very quickly. It's going to be after like day 10 or 11. That's how long it will take for, that 40% mark. So I suppose in theory you would say day 11. Now, if you were going to solve that algebraically, you'd put 2,000 in there. And then it's just, if you were to solve it algebraically, I'd probably cross multiply, and you'll end up eventually solving kind of like a PERT type equation. Just has a little bit more to it stepwise. But that certainly goes over the only new topic that does show up in section 3.5, and that's everything we'll cover first semester.